whatever you think the answer is going to be, whatever one like immediately makes sense to you, that's not the answer. It's going to be the opposite one. So radiation can mutate you, giving you deformities. So every movie you've probably ever seen, somebody gets radiation and they like something happens to them and they like grow a third arm or something weird like that. No.
RoboCop.
If you were exposed, RoboCop was exposed to chemicals, not radiation. So if you're exposed to enough radiation to cause your cells to deform to make you grow a sixth finger on your left hand, you just die. You don't get a chance to grow that extra digit. You just die. So false. Sleeping next to somebody gives you more radiation than X-ray of your hand. Yeah, you're radioactive. So if you're sleeping right next to somebody, then you're going to expose that person and then expose you to the radiation that's coming off of your body. So obviously, sleep alone in a room that has lead blankets. That's my advice. Or not. Okay, so this says recent, but again, I think this quiz, did I even put no, this thing's like 40 years old, 30 years old, something like that. So 1.5 tons of plutonium from France to Japan is the equivalent to about 1,000 oil tankers. So first off, how big do you think 1.5 tons of plutonium would be? How big would that object be? Question.
Like not very big because it's very dense.
Not very big because its density is in top 5 of everything on the periodic table. Okay? So we're talking about something that's the size of a big book bag, a small suitcase. All right, so now how does that thing have the same amount of energy as 1,000 oil tankers? I put that picture of the aircraft carrier up. It's 3+ football fields long, 30 stories high, and the oil tankers are bigger. So what's got more energy? Did you guys put down true or false? Come on.
Oh.
I mean, I'll go look. I'll start randomly pulling up people's homework.
I can't remember.
It's true.
I'm opening up my assignment now, sorry.
That plutonium is going to have more energy than the oil tankers, even though it's so much smaller. Can you, nice. Which, could somebody give me a reason? A quick reason?
There's a ton of energy in it.
No, it's not a good answer. It's because the plutonium is going to use its nucleus. And the oil is going to use their electrons. And they're like third graders trying to play football with NFL football players. I say third grade because I think that's the youngest grade you can be to play football. At least it was when I was a kid. Some TVs and computer screens emit radiation that can cause cancer. No, that's not going to happen. Many dentures are radioactive. True. They're ceramic, so they come from the earth, so there is going to be some in here. So how about this next one? Go ahead.
Mr.
Yeah.
What exactly implies radioactive? Like, can something with just like the tiniest bit of radioactivity be radioactive?
Yeah.
Okay.
Anything that has any radioactivity in it is radioactive. And anytime go ahead.
When I hear radioactive, I think like something that's like glowing, the classic like trope.
Yeah. They almost never glow because the radiation isn't in the visible spectrum. How about this next one about the irradiation of strawberries to retard spoilage causes the strawberries to be slightly radioactive. So first off, do they actually irradiate strawberries? Expose them to radiation? Yes, they do. Absolutely. They absolutely expose it by radiation. So we're talking about like X-rays. So they'll take strawberries and they'll run them down a conveyor belt where there's an X-ray machine that's just turned on. And so just like the X-ray machine that's at the airport, the strawberries are exposed to this radiation. Now, why are they doing that?
If there's nothing alive in it, it won't spoil as fast, right?
They're trying to kill the mold spores on the exterior of the strawberry. You okay with that? So if that mold spore is there, it doesn't matter if it's dead. If it's alive, then obviously it's going to turn to mold. So how do you get strawberries this time of year from Mexico? Well, they irradiate them because if they didn't, they would never make it to you. They'd never get to the grocery store without being spoiled. Strawberries do not last very long off the vine. I mean, you can have a red strawberry on a strawberry plant, and that thing can last days and days. Like, could last, I mean, as long as a bird isn't eating it, could be there for 10, 12 days. Nothing's going to happen to it. The moment you pull it, the strawberry has now lost its immune system. The plant was providing its its microbe response, and now it's not connected to it. So the strawberry is dead. So it doesn't matter that the strawberry is getting hit with this radiation because it's already dead. And you're trying to kill something that's alive on it. So are the strawberries actually radioactive after they run through the x-ray machine? Are you radioactive after you get an x-ray? Is your luggage is your wallet radioactive after it goes through the airport x-ray machine? No.
I guess.
No, absolutely not. 100% no. When you if it's pitch dark in a bathroom in your house at 2 o'clock in the morning, you flip the light on, go to the bathroom, and then you flip the light off. Are you glowing for a while after the light gets turned off?
No.
No, but I'm blind.
No, but the radiation, because the radiation is gone, it doesn't persist. So we'll talk about why that's the case soon. All right, living a mile from Chernobyl nuclear reactor during the accident would likely cause an earlier death than being 5 pounds overweight. What do you think?
False.
The 5 pounds or the Chernobyl? Which one's worse?
Overweight.
It's the 5 pounds. The 5 pounds, that's usually the amount of cholesterol, bad cholesterol in your bloodstream is usually associated with the by pound per person overweight. And so if you follow 5 pounds on the chart of how much very low density lipoproteins you have in your body and how that equates to an early death, being 5 pounds overweight is worse than being a mile from Chernobyl because the blast wasn't a nuclear blast. It was a steam explosion that spread nuclear material all over the place, but not a mile away. That stuff didn't make it a mile. I mean, some of it did in the atmosphere, but as soon as you saw that happen, people just left. All right, organically grown tomatoes are not radioactive. What do we think?
False.
False. It's false because it's got carbon in it, so that means some of it's carbon-14. So some of it's radioactive. Radioactive waste with a half-life of 1 trillion years is even more difficult and dangerous to deal with than something with a half-life of 24,000 years. What do you think? Trillion worse than 24,000?
Effectively, because we're humans, does it matter?
That's the answer. The answer is no. How long have humans been writing stuff down? Like 5,000 years? We're at 24,000 years. So are we talking about a long time? Yeah. I mean, you live maybe 100 years, 80 to 100 years. So 24,000 years is eternity to you. So if we needed to dispose of radioactive waste, it's going to take we have to think about the fact that this is basically forever as far as humans are concerned. We're doing a very bad job of this. The Chernobyl accident has resulted in a bunch of deformed farm animals being born. No, not the case. If those farm animals were exposed to the point where they would be deformed or produce deformed children, they just died. Transportation of fruits and vegetables will likely cause more deaths over 20 years than transportation of nuclear wastes. What do you think?
Yes.
Why?
I don't know. It's just a gut feeling.
Because more people transport fruits and vegetables than nuclear waste.
Because the guy driving the onion truck from Tri-Cities to Portland is not the best truck driver in the world, but the guy driving the nuclear wastes is the best truck driver in the world. He's also being tagged by people meaning there's somebody in front of him and behind him and possibly aerial surveillance depending on what's going on. The route has been set, meaning that that person has to follow this particular map and can alter that in no way. Again, the guy driving the truck of fruits and vegetables just might run you down, but the other guy won't ever have a chance because they'll have closed the road and he won't have anything to hit. All right, a pound of plutonium dust dispersed over a city would likely cause 100,000 deaths. So this is the type of question where I would like to say I would call BS on it immediately and debate, because I would say city, does the city even have 100,000 people in it? So the question is sort of like dumb right off the bat. And the answer to this is no. It would likely cause some deaths, but certainly not 100,000 deaths. And the deaths wouldn't be immediate. They would be a person's life has been shortened by X number of months or years. All right, 3 Mile Island nuclear accident will ultimately result in over 1,000 people dying of cancer. You probably don't know what 3 Mile Island accident is, but the answer to that is a no. It's the other.
I don't think someone was just dumb about, like, the guy who was supposed to watch it so that it didn't overheat was
No,
being stupid.
nope. We'll talk about it, but nobody was being dumb. Okay. What else we got? Didn't we have? So I just grabbed this one just so you got another homework. Radioactive waste remains forever. Pretty much. I mean, not forever, but pretty much forever as far as humans are concerned. People living in Denver, Colorado are exposed to more cosmic. Yes, true. Radiation from tanning beds is more harmful than radiation from the sun. Well, that's a depends. Are you outside in the sun all the time? It's totally about time frame. So usually the people that are in a tanning bed, they're in a tanning bed. Why?
Because they can't get a tan from this. They don't want to be outside and get a sunburn.
They don't have time to go out, and it takes longer. That's mostly it. They work in an office. They don't have time to get out. It's dark by the time they get home, kind of stuff. So they go to the tanning bed. So the tanning bed is going to be way more harmful because it's a high level of radiation that's being directed at the person. If you're exposed to radiation, you'll develop cancer. You're being exposed to radiation right now, constantly. That blanket's not helping anything. So the deal with radiation is every single time you get hit with something radioactive, it could cause cancer. Every single time. But the end result is it almost never does. Suntans are the result of skin damage from the sun. Damage? It's not damage. Does anybody know what? I feel like one of you guys did this for a paper. Am I wrong? Or somebody writing a paper about melanin? Must be the other class. Suntans are the result of vitamin D being activated because you're being exposed to UV, and it's your body trying to protect itself by changing its color, putting more melanin in your skin, which melanin stops you from being damaged, sunburn, which is why people that are from Africa or black people in the United States they don't get skin cancer. That's not 100% true. They could get skin cancer underneath their fingernails, on the pads of their feet, and sometimes on the pads of their hands, but very rare there. On an arm or something like that, forehead, no. They just don't. It doesn't happen because their skin is totally protected.
Can't they still get burnt though?
No, I mean yes, but they're not going to get radiation. They're not going to. They are protected from skin cancer with the exception of those places that I just talked about.
Okay.
If you have a friend that's black and they have a weird black mark underneath their fingernail or underneath their toenail, that's dangerous as hell, and they need to get that thing pulled out immediately.
What's the worst place to live when it comes to like sun radiation?
Tibet, probably. Most radiation we are exposed to is man-made. No, not true. Living near nuclear power poses less risk of radiation than living in a home with high radon levels. No, high radon is super, super dangerous. You should keep track of the number of medical x-rays and scans you've received. Yeah, that'd be a good idea. Exposing food to radiation makes it radioactive. I should have read all of these more carefully because that's a terrible question. Because radiation can be multiple things. The radiation that they do expose food to is not going to be radioactive, but you could expose it to radiation that would make it radioactive. All glow-in-the-dark stuff contains radioactive sources. No. Radiation was discovered during World War. No. Radiation exposure. No. Cigarettes are a source of radiation exposure. True. Children are more sensitive to radiation than adults. Absolutely true. The younger you are, the more it is. What is that up there? That's really weird. Okay. So let's go here, make this bigger, go here, go. I don't know. Oh, I'll stop sharing this for a sec. And then 23, no. Notes. Control A, delete, and then nuclear. Print out. What? You can't open that? Why can't you open that? Control A, Control C. Come back over here, Control V. That's really weird. Did I lose all the pictures? Looks like I lost all the pictures. All right, lame. I can really do that. I guess I'll just go with this. All right. Share. Screen 2. Okay. So we're going to talk about radioactivity, and we're going to talk about nuclear chemistry. So first off, what was the definition for chemistry?
Electrons doing stuff.
Studying properties of matters and electrons doing stuff. For this set of notes, we don't care about electrons. Electrons and where they are in orbit, that kind of stuff, it's not important to us. We don't, radiation, the radiation that we're talking about specifically deals with the nuclei. And so now we're talking about the power that's stored inside the nucleus as opposed to the stuff that's stored in the electrons. What fundamental force would you say electrons have? Of the fundamental forces of nature, I'll say gravity is one of them. What about the electrons?
Chaos?
No. A force. No, you absolutely can't go outside.
Oh, okay.
I gotta wait till class is over.
Movement would.
That's not a force.
Like the four forces of nature.
Yeah. Which one of the four forces?
Strong and weak nuclear force.
Okay, so the electrons don't deal with strong and weak nuclear forces, but that's the one that the nucleus deals with. So what are the electrons? What are those fundamental forces do electrons deal with? Electrostatic. So positives and negatives. So the positives and negatives have a certain amount of, I don't know, ability to interact with stuff, and the nuclear is orders of magnitude larger than that as far as the amount of energy that you have. So the nuclear force itself is a much more powerful force than the electrostatic forces. But the difference is the nuclear forces only have the ability to act over a very, very small distance, like 10 to the negative 15th meters. I can't use it to like hold the materials together. Hey, stop. I can't use it to hold materials together to like make a bridge. That's not how it works. Okay, so we're dealing with the nucleus. We're not dealing with the electrons. So why are things radioactive? Radioactive, since it's coming out of the nucleus, we're talking about the nucleus itself being radioactive. And what that means is the nucleus is unstable. So how do I have an unstable nucleus? We discussed this the first term. Does anybody remember what it was?
The number of neutrons?
More specific than the number of neutrons.
Balance of charges.
Not charges.
Or what is it? Ah, shoot.
The ratio of protons to neutrons. Depending on what that ratio is for each atom, that atom could be radioactive. So if you have too many neutrons, you can be radioactive. If you don't have enough neutrons, you can be radioactive. You need to have like a baby bear number of neutrons. It needs to be just right. Stop yelling. So the other part with that is anything that has more than 83 protons in it, it does not matter what the neutron ratio is. It's radioactive. So if you find 83 on your periodic table, is bismuth, and so polonium and everything past that, no matter what the ratio is, it's radioactive. Okay, so we're at 83, you move over, you get to radon, then you skip all the way down to 89, which is AC at the very bottom row, and then you go to thorium, protactinium, uranium, and whatnot. So anything over 83 protons is radioactive, anything with a bad ratio. And I can't say that the ratio is a specific number because it varies based off of what atom we're talking about. With hydrogen, having no neutrons is fine, having 1 neutron is fine, having 2 neutrons is radioactive. With carbon, having 5 neutrons is fine, 6 neutrons is fine, 7 neutrons is fine, 8 neutrons radioactive. So it just depends on the substance. So to be specific about what isotope we're talking about, we could write it in these different ways, type 1, 2, and 3. So type 1 was developed first. It just tells you what the mass number is and then tells you the number of protons. They went to type 2 because writing that 6 to the bottom left of the carbon is redundant, because any carbon atom has 6 protons in it. So you don't need to really write it. And then the last one is they just switched it, so it was C-12 to tell you that this thing is a carbon atom with a mass of 12, and since it's carbon, you know that it's got 6 protons in it. The last one was actually forced on physicists by secretaries. Does anybody know why? Besides me, who has used a manual typewriter? One person?
It's a pain.
2 people. Try to do a subscript with it. Try to do a superscript. So you have to half space, then you have to grab the roller and turn it a half, and then hit the number, and then turn it back a half, not a full, because you'll be in the wrong spot. It's just a pain in the butt. So the secretaries are like, we're going to put 12-12, and then that's going to be carbon 12. And they're like, well, why are we doing this? Do you want to type it? No, that's okay. That's pretty much how the conversation went. So from that point forward, just in a paper, it's written as C-12 instead of superscripted 12 space C, just so it's easy to word process. Okay, so let's talk about 3 types of radiation and then a couple of other types of radiation. So there's an alpha decay, which is basically a helium nucleus coming out of the nucleus of another atom. A beta decay, which is a high-speed electron coming out of the nucleus. I know that doesn't make any sense, but we'll talk about it in a second. And then the gamma decay, which is just a type of light radiation, and that light radiation comes out of the nucleus because the nucleus is excited. Right. You need to go in your bedroom. Okay?
Why?
Because you're too loud. Because you are. Okay, so let's start with the first one, alpha decay. So what we have there is a plutonium, and all plutoniums have 94 protons, and this particular plutonium has 239 total mass. So 94 of that is protons, and the rest of it is neutrons. So this is an alpha decay, and what we're saying is an alpha particle comes out of the nucleus, and an alpha particle is 2 protons and 2 neutrons, which is why it says helium there, because it's the same as the helium nucleus. So 2 protons, and then the total mass is 4 because the other 2 mass is neutrons. So all you have to do is some subtraction and some addition, or sorry, just addition in this case. So I've got 4 and I've got 235, and those together make 239, and 2 and 92 make 94. And I'm going to hate this, aren't I? So the top has to add and the bottom have to add up. You okay with that? So that nucleus just got a total mass of 4 lighter, and it lost 2 protons. Okay, so let's talk about the beta decay. So the beta decay, I said, is an electron that's coming out of the nucleus. So how's that possible? There aren't any electrons in the nucleus, are there?
Doesn't a neutron break apart?
A
Somehow?
proton is this big particle, and if I physically connect an electron to it, what happens to the charge of this thing?
It's neutral.
And that's a neutron. So a neutron is actually a proton that has had an electron embedded in it. So if this thing is radioactive and this electron leaves, what did I just do to the particles in the nucleus? I converted a neutron into a proton. We're okay with that? Did the mass number change? It's still a proton, and the proton and the neutron are equivalent to a mass of 1. But what did change is I increased my internal charge by 1. So if I'm looking at this example here with the carbon-14, so 0 mass comes out. So I've got an electron with a 0 here, and then the neutron, or the total mass here, is still 14. But look what happened to the proton number. It went from 6 to 7. If I added 7 and -1, what do I get? 6. So mathematically it makes sense. And then the last one down here, this is the gamma decay. No actual physical substance comes out. It's basically just high energy light. And the nucleus is excited. Wow. The nucleus is excited, and it gets rid of some of that excitement by dumping a high energy gamma ray out of it. So it still stays technetium, and it still has a mass of 99, and it still has a total proton number of 43. And then some other types, positron emission. So a positron is actually a positively charged beta particle, which means it's a positively charged electron. Might not have known those exist, but they do. Has anybody heard that term positron before? Maybe in a medical sense?
Don't they specifically have positron emitters? I can't remember what they're for, but
Yeah, it's called a PET scan, which stands for positron emission topography. So it's just another type of scan, like an X-ray, or pretty much just like an X-ray.
what can it see that an X-ray can't?
The X-ray basically just penetrates because it's just light. So in the
Yeah,
same way,
so-
if I hold a piece of paper up and I shine a flashlight through it, the light just goes through it. But if I shoot tiny BBs at this, it won't make it through the paper. And so you get a feel for what the surface looks like.
Doesn't the PET scan also show brain activity?
It can show brain activity, but so can an MRI. Okay, electron capture. It's exactly what it sounds like. One of the 1s2 electrons is actually absorbed into the nucleus, and it turns a proton into a neutron. So the proton number goes down. The mass number stays the same. So if I was element number 15, I become element number 14 because I turn one of my protons into a neutron. And the neutron emission, literally the nucleus just kicks out one of the neutrons, and it becomes one mass unit smaller, but it's still the same type of atom, still the same element. So those are some some types of radiation. What's the major difference between the gamma decay and all the rest of these?
Is it the fact that the it doesn't lose mass, or that it's because it's just energy, or
Yep. The alpha, the beta, the positron, the electron capture, and the neutron emission, those are all particles, actual physical objects that have mass and volume. And the gamma is just light, it's just radiation. So it doesn't, you can't capture it. It's not an object per se, it's just pure energy. Okay, so let's have a pretty long discussion about the electromagnetic spectrum or electromagnetic radiation. When I say electromagnetic radiation, what I mean is light. So when we think about light, we think about this. But that's not what light encompasses. So what else does light encompass besides the thing that you can see when you turn on a lamp?
Color.
No, that is the stuff that's in a lamp.
radio waves? And
There you go, radio waves. So that's an example. So we've already talked about gamma rays. We've already talked about X-rays. Those things are just light. So all the radiation that isn't these things here, alpha, beta, positron, electron capture, and neutron emission, all of that radiation is electromagnetic spectrum radiation. So besides X-rays and gamma rays, what other kind of radiation would you say that exists?
microwaves?
Okay, microwave is a form of radiation. Are you scared of your microwave? No.
My dad is.
Your dad is?
My dad specifically said that he doesn't believe in microwaves.
Okay, well, you don't need to believe in something that actually exists for it to actually exist, so that really doesn't matter. I mean, I'm confused. Do you own a microwave?
No, we don't.
Has he seen a microwave before?
Yeah, we used to own a microwave.
Okay, so he knows it actually functions.
Yeah.
So that it exists. Cool. All right. So don't ask Annika's dad about radiation. Okay, so I'm glad that nobody's afraid of their microwave. That's good. It's like pretty much anything. You should be afraid of things at a certain level. Everything can kill you, right? I mean, this cap to my soda stream could kill you, right? If you
Yes.
tried to swallow it and it lodged in your esophagus. Okay, so everything's going to kill you. Can the microwave kill you? Certainly. Can it kill you in the way that Annika's dad thinks it's going to kill you? No, it can't. So think about light that you see and think about light that you can't see. And somebody else give me another type of radiation.
Infrared and ultraviolet.
Okay, ultraviolet. So great. Ultraviolet's going to cause skin cancer and actually absolutely can. Infrared cannot cause skin cancer. It is not physically possible. So give me an example of infrared in your house.
Your electric cooktop?
When you turn on your range to boil water, the burner itself, unless you have a specific type, it turns red if you turn it all the way up. But you don't have to turn it all the way up for it to be hot, right? It doesn't have to turn red. So if you turn it up to, if your scale goes from 1 to 10 and you turn it to 3, it's not going to turn red. But is there something coming off of it? I mean, would you turn that burner on 3, walk away, come back 5 minutes later and just put your hand on it?
No.
No, because it's going to be like 250 degrees. Can you see anything? Can you sense anything?
You can
Besides
feel the
heat.
heat.
You can feel the heat.
Yeah.
So what is it that you're feeling? You're feeling infrared radiation. Can that infrared radiation give you cancer? Should anybody be wearing a lead vest while they're boiling water? Should anybody be wearing a lead vest while they're standing next to a campfire? No, that's ridiculous. Okay, so what I want you to understand about electromagnetic spectrum and about electromagnetic radiation, it's two acronyms for the same thing, is it's light. And some of the light is dangerous as it is, but a good huge portion of that light is not dangerous in the way that people think about when they hear the word radiation. So not all forms of radiation can cause cancer. So this is the spectrum itself has a wavelength that's composed of a magnetic field and an electric field. So the magnetic field is perpendicular to the electric field. We know this because we passed light through electric fields and magnetic fields, and it gives a signal in the same way that, like, if you held a string tight and yelled at it or blew a trumpet at it, that the string would vibrate. Okay, so this causes a detection field of an electric field and a magnetic field to vibrate, and it would look like this, and they're perpendicular to each other. We measure light in two ways, using wavelength or using frequency. They're basically the same thing, but they're inverse of each other. So the wavelength one is super easy. I just measure from one point on a wave to the same point on the next wave and measure how long that is, and that's wavelength. So usually people use the crest of each wave, and you can see that little symbol that looks like an upside down Y. It says equals wavelength.
Yeah.
That's the lowercase Greek letter lambda, and that's what people use for the symbol for wavelength. The symbol for frequency looks like a lowercase cursive V, and it's the lowercase Greek letter nu. And so we can talk about wavelength and we can talk about frequency. So here's the rainbow, Roy G. Biv, and you can see that the red has a longer wavelength than the orange. And the orange has a longer wavelength than the yellow, and the purple's wavelength is the shortest. So in this case, the wavelength that's the longest is red, the shortest is purple, and then the opposite. If I count the number of waves that have passed by a point in a certain period of time, I'm going to count more purple waves than I am red waves. So you see that thing of unit time? I can see 1, 2, 3, 4 full purple waves have gone through and cycled, and I haven't even gotten half of a red wave yet. So the frequency for the red wave is much less than the frequency of the purple wave, and that's based off of the length of the wave. And the reason that this works is because this is light, and so the red and the purple are both moving at the same speed. They're moving at the speed of light. Okay, so as long as they're in the same medium, they're moving at the same speed. So this is a high frequency, this is a low frequency. Their relationship is inverse to each other. And so the shortest wavelength is going to be violet, and the longest wavelength is going to be red within the electromagnetic spectrum of visible light. All right, so let's talk about this table. So I'm going to give you 20 seconds to look at this and understand what the axes are and a couple of the things on there.
Who remembers this from calculus?
Shut up, Sheen. We're not all perfect like you, okay?
I'm sure Isaac remembers.
Hi.
Hey, they're busy.
Oh.
Hello.
Hi, Penelope.
Hi, Penelope.
Hi.
All right, I'm just going to sit on you. This is not going to feel good.
No. Ow.
Oh, you want to get up? Okay. Okay, so first off, what I want you to notice is the common names for some of these waves. We have radio waves on the left, and we go through microwaves, infrared, visible light, ultraviolet, soft and hard X-rays, and gamma rays. So, yeah,
Sorry. I was gonna say, what's the difference between soft and hard X-rays?
you tell me.
One is really soft, like clay, and the other's like a rock.
All right, I'm muting you. Tell me off of this table what the difference is.
Well, soft is bigger.
Soft is bigger and hard is smaller wavelength. What we're going to find is which end of the spectrum are you scared of? Left or the right?
The right, because
Right.
it's
The right is terrifying. I don't ever want to be exposed to gamma rays more than I'm already exposed to gamma rays. Gamma radiation is the stuff that, and we talked about earlier, the movies where the person is out in space and they face the sun. The gamma rays immediately cook them.
Isn't that what that giant T-Rex looking thing eats? Why can't I remember its name? The thing that came out of the ocean and it's like a giant dinosaur.
Godzilla?
Godzilla.
How do you forget what Godzilla is?
I don't know. Okay, listen. Isn't that what he eats though?
No, he eats Tokyo.
No. Okay. Yeah.
Hmm.
He's like powered by gamma rays.
I don't know.
I thought that was Mothra.
That's
No.
that's Hulk. You're talking about the Hulk.
Hulk.
I'm not talking about the Hulk. I'm talking about
I'm just talking about a thing of fiction that is powered by gamma rays. That would be Hulk.
yeah.
I don't know about Godzilla. I can't talk to that. I know the mythos comes from the nuclear explosions at the Tahiti Islands, but outside of that, I don't have any Godzilla facts. So
Godzilla is said to have feed off radiation and hibernates in modern times.
cool. Okay, so why are you scared of the radiation on the right, but not the radiation on the left?
Because we're used to the radiation on the left.
No. I mean, maybe, but no. What's the bottom of this chart have on it?
Energy of 1 photon.
Okay, so what's the difference between gamma rays, energy per photon, and say radio waves?
There's very little compared to a lot.
So we're looking at 10 to the 6th per photon. That's a ridiculous amount of energy. And we're looking at visible light. So find visible light here. We're at like 1-ish electron energy of a single photon in electron volts. And this is effectively 1,000,000 times more powerful per photon of light. So why is this side more dangerous? Because this side, the shorter the wavelength is, the higher the frequency, the more energy we've got. So the hard X-rays have more energy in them because their wavelength is shorter. The soft X-rays have less energy because their wavelength is longer. And as I move this way across the table, the wavelength goes up, the waves get longer, and the energy drops precipitously. Okay? So where on this table should you be worried? Now, what radiation, let's say length in wavelength meters, are you worried?
10 to the 9th ish, 10 to negative 10.
No. Here. You're worried right there. Do you guys see that? Can you see that arrow I just drew? Yeah? Why am I saying right there? And how should you already know that?
Viruses are right there.
What's right there?
The viruses.
Oh, no. That's funny. No. That's just
Oh.
giving you like this is the wavelength, this is the size of these wavelengths. It's not trying to say that the virus has anything to do with it. But that's going to be the next Trump conspiracy.
Is it because we know ultraviolet causes cancer?
Ultraviolet has enough energy to break a chemical bond. So I want this to be as clear as the sun noon in August with no clouds. That if you cannot break a chemical bond, you cannot cause cancer. Period. There is no one is debating this. There's no scientific debate about this. Yeah, Kalina.
So microwaves don't cause cancer.
So hold up a second. True, but let's talk about this for a sec. So the amount, the wavelength here is I'll just say we'll say 10 to the negative seventh, okay? So that equates to about 10 electron volts. So if your photon, your light, doesn't have 10 electron volts, it literally cannot break a chemical bond. So we're talking about a carbon-carbon bond. What can bust that bond apart? Something that has 10 or more electron volts in it. So if you don't have 10 or more electron volts, you can't break that bond. We okay with that? Everybody all right with that? So if you walk out onto your driveway, and if you've got, let's do a better analogy. If you go to the Hood River Bridge illegally as a pedestrian and stand in the middle of the bridge and start stomping on it with your foot, are you going to break the bridge?
No.
Does it matter how many times you stomp on the bridge? Let's say you're out there, you don't get arrested. For some reason, you can last for days and days without eating or sleeping or drinking. And you stomp on that thing 5 million times. Are you ever going to break the bridge right there?
No.
No. But what if the Hulk comes out and steps on it hard one time? So once I've passed violet, the color violet, that is our cutoff point. That is the end of the road. As soon as I get past violet and the light becomes invisible to my eye, everything past that can kill me. Everything before that cannot kill me, radiation-wise. Cannot kill you. Period. Cannot cause cancer. Physically impossible. In the same way that you're standing in the middle of the Hood River Bridge, jumping up and down on it, trying to break it in half. You will never do that. And any radiation whose wavelength is purple length or longer cannot cause cancer. So having said that, look at this chart again and tell me what's on that list of things that cannot cause cancer.
And radio.
Sources, AM radio. What is that RF cavity? What radiation does this use? What radiation does your Wi-Fi use? Where is that in this spectrum? It's right there. So for all the crazy people who think that cell phones can cause cancer, what should the answer to that be? Look at where it is. Your cell phone radiation, the photons that come out back and forth from your phone to the tower, have an electron volt energy of 10 to the negative 7th. What did we say we needed to cause cancer?
10.
10. So how much smaller is 10 to the negative 7th than 10? A 100 billion times less energy in the radiation in your cell phone than in ultraviolet light. And ultraviolet light is the minimum amount of energy that can break a chemical bond. So can this break a chemical bond? No. So when you're standing in front of your stove and the stove's on and it's hot, should you be worried about cancer? No. Should you be worried about burning yourself? Yeah, that's not the same thing. That's not cancer. That's just dumb if you put your hand on that. They're not the same thing. You cannot put your hand on the top of the stove and get a 3rd degree burn and go to the ER and get cancer from that.
What's the ALS?
What?
What is the ALS?
I
Isn't
don't
that a
know.
collider?
I think yeah, it looks like that's the collider that's in where is it? Switzerland? Switzerland? Is it in Switzerland? That's CERN, the Atom Smasher.
I think I forgot where it is.
I think it's in Switzerland. Maybe Austria. I don't know. Right there next to Germany, in between Germany and France, sort of. All right. So, what's our take from this little thing right here?
That I have material to prove my grandmother wrong.
Sure. She's still not going to listen to you, but that's okay.
Oh, I know she won't, but at least I can try, I guess.
Could a microwave actually cause damage to you?
Yes.
How could it cause damage to you?
Someone threw it at your face.
A microwave could also boil the water that's in you.
So if you jury-rigged the door, so the door was open and the microwave still turned on, and you put your hand in there, it would be as bad as your stove being on high and you putting your hand on it.
Well, I know there were people that put like dogs in microwaves when they first came out.
H. Don't
What?
say that.
People were stupid. They thought they could.
Nobody asked for that.
Thank you.
Nobody at all.
Yeah,
Nobody.
the dog definitely didn't.
I mean, I read some things on OSHA violations where people made their way into lumber microwaves and then somebody figured it'd be a good idea to turn it on.
Yeah, isn't that the beginning of Kick-Ass?
Oh my God, you're right.
They use the microwave to cure the wood, meaning they're trying to get the water out of the wood, and yeah, you could use a giant microwave to do that, and it could absolutely kill you. But that guy that died in that microwave, guess what? He didn't get while he was in there.
Answer.
He didn't get cancer because it's not possible. Okay. So some of these wavelengths are ridiculously long, like more than a kilometer, 10 kilometers long, meaning the wave will go 6 miles before it comes back up and peaks. So these things, that there are different aspects of these different wavelengths of light, but the things that you should think about are the stuff on the right hand side, for the most part, doesn't have very good penetrating power, and the stuff on the left side usually has really, really good penetrating power. Why would that be the case?
More energy?
So the stuff that's on the right hand side has more energy in it. So as it enters an object, what is it probably going to do? It's going to start breaking chemical bonds. And the moment it's broken a chemical bond, the energy is gone. It's used. So tell me about cell phone radiation.
Not break photons.
It doesn't break chemical bonds, so it has good penetrating power. So is this, I know the closest tower to me is this direction. Shh. So if I put my cell phone right here on my back and the tower is over there, what's happening? My phone is communicating with that tower right now, so what's going on?
The radiation's going right through you,
The
right?
radiation's going right through me. Am I freaked out by that? No, because I know it can't do it. It can't break a chemical bond. And the other thing with that is all of those radiations are going through you. Like if you actually had a radio and you turned it on, how are you hearing a signal? Because that radio is going through the house. It's going through you. It's going through trees. It's going through stuff. And it has that long wavelength has good penetrating power. Does anybody know where the avalanche beacon is on this list? It's way here. Why?
Maximum range.
Maximum penetrating power. Because of the penetrating power, you get maximum range. So if I'm buried under 30 feet of snow, but I'm somehow still alive, activate my avalanche beacon, I need that avalanche beacon to send its signal through the snow and get out. So this little sliver here is highly protected by the FCC. Stop. What do I mean by highly protected?
You can't broadcast on those
If you're
things.
caught broadcasting on it, you'll go to jail for like 20 years. So there used to be a thing where people would pirate radio stations, which means they would find a radio station that people listen to a lot when people listen to radio a lot. And they would put it in a place high and have a powerful signal that would override the signal coming from, say, Portland. And then they would be able to everybody would be listening who was on that frequency. And that used to be a thing. And it's not like it ever happened here, but it would easily be something that could happen in, say, New York City or Los Angeles, because there's a lot of places to hide there, and there are a lot of different radio stations, and you could pop on and spew whatever it is you want, and you know people are going to listen to it because it's an active band. The different cell phone towers, they basically run off of the same electromagnetic spectrum. We switched out of an old version a long time ago, and they went to a more high penetrating one, and that also will allow for more information to get transferred. And then obviously will allow for COVID to be injected directly into somebody's body. Please know I'm being stupid and sarcastic. That's the thing right now. And if you don't know that, it's 50 plus cell phone towers that send out 5G have been burnt to the ground, because there are actual people that think cell phone radiation causes the COVID virus. So let's think of that for a second. We're talking about pure energy in the form of light that manifests itself inside of my body to miraculously create a living organism. Well, kind of a living organism, not really a living organism, but sort of a living organism. Yeah, so cells being created out of nothing. That sort of violates many, many things in chemistry, right? Matter cannot be created nor destroyed. Yeah. Yay, Trumpers. Okay.
How you can even like.
It's hard to have a conversation with somebody about it because they don't. The first thing I say is you need to take a science class. Period. Take a chemistry class, because we can't talk, right? I mean, we might as well be speaking completely different languages. That's how far apart we are on this. Like, you don't know enough for me to even start talking to you about this. That's how bad it is. And again, could you imagine being in your house and all of a sudden, wait, my phone doesn't work anymore? Like, it doesn't work, and it's not going to work for a couple of months because some crazy guy burnt my cell phone tower down. The tower that gives me signal in my house has been burnt to the ground, and now my phone doesn't work because they think something completely, utterly ridiculous. And it's not insignificant. We're talking about 50 plus cell phone towers that are hundreds of thousands of dollars a pop and take a ridiculously large amount of planning to get even installed. Like, they've been trying to install that one next to Windmaster for how long? 6 years? 7 years? Allison, are you being beat up? Are you okay? You're gonna survive?
That was necessary.
Okay. Okay.
Those
So
people that like they know it, but they don't want to believe it because they think it's fake.
we'll talk a little bit more about this on Thursday, and then move on to some other stuff that is heart free. Hearts free. How do I erase stuff? There we go. All right. Have a good day.
Thanks, Rob.
Stop.
Thank you.